Okay, the second part of this chapter is again mathematically quite small, but it's all about the explanations. So we're going to be looking at stability, why certain things, for example, fall over. We can get them to balance so they don't. I don't think I'll be managing with this, but I could if I got a long meter stick. I could actually just get that to balance on my hand because of the way that we use the forces. Oops, he says, there we go, that's pretty much balanced. Okay, so how it works is all to do with the moments. We're going to assume that the weight of everything is everywhere throughout it. So if we take a 50 centimetre ruler, then fairly obviously the middle is at 25 centimetres. So just to give you the idea of centre of mass, this obviously is a uniform ruler, it's the same width, it's the same thickness, etc. So guess where the middle is? The mass is centred in the centre. You can check because if there is too much weight on one end, what will happen is that weight will push down on that finger so it doesn't, so it's now my right finger, or your right view, and it will stay there when there's more weight on it until it keeps balancing. So as I slide those in, you're always going to get an equal amount of weight on each side until you get to the point where they balance neatly, roughly. I'll tell a lie, it's at 49.5. So it roughly in the middle. Okay, then that will always work. So if you try it with something long and it's nice and even and you slide them in, you'll always find that it just balances on that midpoint. When it's not the same shape, where we've got different thicknesses, it's going to bend, it's going to balance in a slightly different way. But when it is actually balanced, which we'll put on my finger there at the moment, when it's balanced, it's because there's an equal amount of turning effect on each side. It's got all of the mass evenly spread around it. So it's not going to be heavier at one end. That heaviness, if it is more massive at one end or more dense at one end, that will be a shorter end. It will have to be closer to the middle of that item, whatever the item is. So balance is all about that. Mathematically, it's fairly straightforward. All we need to do is use the law of moments, which is highlighted here. So what we're going to do is, in terms of thinking about it, mathematically we say sigma for sum, but we have the forces that are clockwise, we're going to have the distances that are clockwise, and they will always equal the sum of the anti-clockwise and distances and forces. So, e.g., we could have down here several things. Now I've used S in this version, it doesn't matter too much. S is displacement, so again it's slightly dodgy, or it can be, so just be wary of this. But this one here, that force 2 is going to cause a bit of a twist. Force 1 is going to cause a bigger twist because it's a bigger distance. So we've got two turning effects, both turning it anti-clockwise. But over here, we've got two turning it the other way. Okay, so what we've got going on is we've got more than one moment, but both of the twisting effects from all of those, so the ones turning it clockwise and anti-clockwise, must be in equilibrium. They must add up to 0. So what we can say, we won't do the adding up to 0 bit, but what we can say is that we use that clockwise bit, so this is 3 and 4 over here. We can say that F3 multiplied by S3 plus, and you might want to put brackets just to make it easier, force 4 and S4. That will give me my sum. Both of them, all we just keep doing is adding more and more and more. If someone sat on this seesaw, then we'd add on their force and their distance. One's in the opposite direction. We have F1 distance 1, sorry, S1. And we're going to add on the second one, which is force 2, S2. Okay, and so what we end up with is very simply that plus that will equal 0. but we'll have to get into thinking about which is a positive direction, which is negative, because we need to show that they're different. So what we'll do is instead just make them equal. So F3S3 plus F4S4 equals F1S1 plus F2S2. And if you always lay out your first line of maths in this, so think of this as on one side one direction, here we've got clockwise, here we've got on the other side all of the anti-clockwise ones. You can just put the numbers in, it will simplify down in the next row of mathematics when you put the numbers in, and you can find your unknown S or F, whatever it is you're trying to find. Now, if we're using that as an explanation, then we can use this in terms of why things don't rotate. So, if I put this pen here, it doesn't fall over because the centre of weight, the centre of that mass, is above the bottom. If we put it there, it's above wherever the base is as well, so it's not going to tip over. It doesn't matter where I do it, it's going to have that weight above. If we hang it instead, then what we've got is when we're suspending it, okay, so we're hanging it from that point, we still know that the weight must be central. So I can actually find out where the middle of my pen is by holding it and hanging it. We know that the weight, the centre of all the weight, is somewhere underneath that. So it's somewhere down the centre line, I'm going to say, because it's a nice even shape, and it's hanging underneath that point. So I can find out quite easily where the centre of objects are by getting them to balance. And if I can get it to balance in what we call an unstable way, in theory, if I got it right, I could balance this pen on its edge. Okay? And if we can get it to balance on an edge, just like we do a ruler in your hand, then we can know where that centre of mass is, and it's all about stability. So if the centre of it is over the feet, over the base of it, it's not going to fall over. If we put the centre beyond a certain point, geniusly, it falls over because it's not stable. There is a bigger turning effect, a bigger moment on one side, and that's what makes it twist round, okay, and fall over. So, to fit with the question here, if an object is suspended by, e.g. a thread, it will come to rest with the centre of mass directly below the suspension, because all the clockwise and anti-clockwise moments are balanced. Again, fairly obviously, we try and avoid the word balanced for fairly obvious reasons when we're talking about seesaw-like things. But all the clockwise and anti-clockwise moments add up to a resultant moment. It's a resultant of 0. Okay, so just like resultant forces, resultant moments can also add up to 0. Okay, so notes-wise, that's it. We're going to, in the lessons, explore that a lot more, and we're going to get into some rather more interesting things, because you may not realise it, but we have all kinds of structures that are balancing. If we look at a bridge, for example, that is also balancing. Okay, now the mathematics of that is quite tricky. We'll demonstrate it first in the lesson, but just for completeness in your notes, we're going to work this through. So, if we had a bridge, I'm going to simplify that bridge down to 2 supports, so 2 pivots. Okay, let's call them X and Y so we know which one's which when we're talking about it. They're both pushing up. Okay, so I'm going to call it force 1, force 2, and they're both pushing up because the bridge is pushing down on them. Okay, so those are the reaction. They're there because the bridge has weight, and just like the meter ruler, it's in the middle. Okay, so it's always in the middle if it's a nice even shape, and we'll label that up as mg. Okay, Now, in the demonstration that I'm going to put with this, so there's a demonstration with me with doing calculations with the beam bridge, so you can check this. If we were to put something on the bridge, some sort of mass, then that mass itself, the weight of that mass will also push down, and so that will cause problems. If it's near one end, it's going to push down more on there than it is on there, so F1 will be bigger than F2. So how do we go about calculating this? We need to use two key facts, and they're fairly straightforward. The easiest one is the most important one. Unfortunately, we have to use the not so easy one first. So, just to round it up, I'm going to put in a couple of distances, three distances. So A is from there to there, B is from that force to the middle, and C is from the middle to the other side. So those two add up to that. Those two together give me C. So, the key point is that it's not falling down, it's not moving. So, at equilibrium, okay, we know two things. One, forces are balanced. So, resultant force, can't spell force, equals 0. Okay. We also know the second key fact for equilibrium, the only other facts, so both of these cover it, in that the resultant moment, shorten that to that, moment also equals 0. Okay, so it's not twisting, it's not falling, it's not rising up, it's not moving. So both of those must be true for this to work. So, I'm going to start with 1 because that's kind of obvious, and we won't be able to use it to get the answer, but we can get it to use part of the answer later. So the force is up, there's no sideways one, so up equals down. So in other words, force 1 plus force 2 equals that blob, whatever it is, plus the weight of the bridge. Okay, now if we are going to work this through, I'm going to need to also think about its twisting force. You may think it's not twisting, but if you imagine that and that was to suddenly snap, for example, or snap here, then what would happen to the bridge is it wouldn't fall down, it would twist round. Okay, so it would collapse, still be attached here, and this side would collapse the other way. So actually these also have twisting forces, which is why you have these diagonal beams to try to prevent the twisting. So if we go for the second rule, what we're going to do is choose one of the points. So I'm going to take X as the pivot. So pivot at X. Now what I've got there then is I can measure the forces, 1, 2, 3, and the distances from X. So what I've got is, let's go with clockwise first. So clockwise equals anti-clockwise. So what I've got here is the clockwise one. I've got F times A plus mg. I'm going to have a few letters here, so, and then that distance, so A plus B, okay, and that is the two forces that are making it twist in that direction. The only thing stopping it is this force, so that is going to equal force 2 multiplied by the total distance, which is A plus B plus C, okay. Now we haven't got any numbers here, so we can't really go any further, but it doesn't matter if you do that, or, so very importantly, or just take the pivot at Y, okay, and you can get ahead of me on this, so if you want to freeze the video you can do and then write it out, but for this one, if that's my pivot, then force 1 is pushing clockwise, these two are twisting it the other way round. So again, I'll stick with clockwise on the left. I've got force 1 times A plus B plus C. Okay, that's my total distance. And that's going to equal, this time, I'm going to have that distance to the force. So force times B plus C. That should be multiplying there. And add on the mg one, which is just mg times C. Okay, so if I've got any numbers, if I've got those distances, what I will find is from my known force on the bridge, my known weight of my bridge, often given as mass, so you multiply by your gravity to get the weight. Put all the numbers in, the dimensions in, and you will get the unknown force. All you need to do is then, you could either put them back into the other one to work out the other force, or you could be far more sensible and just go up equals down. So you know that, you've just worked out one of those, you can easily work out the other ones because they just add up. So then use the linear forces, because it's much easier to do the maths with linear forces, to find the unknown second force. Okay, so that's the key bits of maths. That's as hard as they get, and again there's practice questions, but yeah, it's all relates to stability. So here it's all stable, so therefore all the forces and all the result moments are cancelling each other out. Sorry, the forces cancel each other out, the moments cancel each other out. But that links into the stability. So again, I'll add this on because this really is such a short chapter, you might as well put it together. Here's our idea on stability. So this is nicely balanced. It's called unstable equilibrium because the weight, the centre of the weight, the centre of gravity, sometimes called as well, lies over the tip. Okay, so the force is pushing straight down on the tip. There's nothing twisting it around. But if it's slightly to one side, then what happens is the weight is a distance from the pivot, and so it twists it round. If you are on something that's quite stable, it doesn't mean it doesn't rock, but if it tips up, for example, a conical flask, the shape of it is designed so that you've got a big distance and it'll fall back onto the base. So it'll always fall onto the base, whereas something that's quite narrow is quite easy to fall outside of the base and tip over. The last one is neutral equilibrium, and that it doesn't matter what you do. Round pen, for example, as it rolls, the weight is always over the base because the weight is in the middle and the base is at the bottom, so it's always going to be on top. So that's the kind of key idea. What we can do to make things more stable is if we bring this lower, okay, so lower down the shape, it'll actually make that distance bigger, so it'll actually give a bigger turning effect. So that makes it more stable, so we can do a lower centre of gravity. Or we could just make the base much wider, because then it's much harder to lift that up. So if we wanted to tip this over, we'd have to keep tipping all the way until that centre gets to this position above the base, and then it would go beyond. So the wider that is, the more we have to tip it. Okay, so do we do it like that, or do we do it like that? Look how much further I have to tip it to get to the vertical position before it falls over. So the second thing we can do with everything is a wider base, and these are classic in sports. Sports cars, very low and very wide. If you're going to be something where you need a bit of stability, for example basketball, what do? You bend your knees, so you bring your weight lower and you stand with your feet further apart. Archery, another classic one. It just makes you very, very stable. So how do we do it? We do both of these, and the reason is you as you then need to tip further, and that's the crucial bit, before the centre of gravity, so C of G, goes beyond, beyond the edge of the base. Okay, in which case if it goes beyond the edge, it falls over. Okay, Works in reverse if you're floating, so a little diagram on the bottom here, and that kind of idea is again, you've got the weight pulling down and you've got the centre of buoyancy, so you've got a floating upthrust force. So this is upthrust, this is your buoyancy because it's floating in water. Fine if they're basically above each other with a little bit of give or take, but if they get too far beyond each other, then again it will just flip over. Okay, so things like lifeboats, they're designed to have their weight as low as possible, so a lot of ships have a very heavy base and a lot of air space above, but if you overload them, it makes them less stable. So again, that idea of Lloyd's of London floating ships, not overloading them so they sink too far down, because it makes them less stable. Okay, so yeah, we'll go through because it's really about discussion, but those are the two sets of things you need. Descriptions based on stability, okay, and the mathematics of stability. Sometimes quite complex if you have like a beam bridge, as it's known, a flat bridge, but that will be as hard as it gets. For most of it, it tends to be thinking about that, so turning difficult diagrams into something that looks quite flat. So, to give you a hand with that, if we just give you an example of a type of question we've had in the past, you may have a boat that's being pulled or tipped. This is a historical thing, and it's being pulled up by some sort of hook, and that hook is on a beam tower at the side of a dock. Okay, what you've got is a very long beam, so that the people can then pull downwards, and again, they tend to make it easier. They'll have a right angle somewhere, but basically they'll pull it down through, for example, pulley, so that they can then pull it that way. So what we've got is a force and a distance, but we have a bit of an angle. We've got a force and a distance, so again we have our weight pulling down, but it's actually pulling at an angle, so there's your tension really. So again, you've got force and a right angle distance, different distances, different forces, smaller force because it's a big distance, okay, make it easy. But you've also got stuff here, so this acts like a pivot as well. So again, you've got a distance, and you know, you could do some weight and so on calculations here. So again, it's all putting it into the ideas of effectively a free body diagram. So there's my boat. We are pulling up on the boat. We are turning that beam. We have that pivot, and we are pulling in a certain direction. Okay, and that's what you need, not all the artistic impression of here's the wall, etc., and all the detail that just puts you off. Okay, so that's the easiest way to think about things. Again, you can break it down. So keep it simple, draw them as straight lines, and it gets much, much easier. Okay, so practice, practice, practice. Back of the book, there's loads in there, and we'll go through them in class as well to make sure you're happy. Okay, thank you very much, guys.